All of the problems recorded in my videos can be downloaded at statisticsworkbook.com. If you go to the website, click on the PDF, and you can download a copy of the entire workbook for yourself. Also on the website, you'll find access to all of my videos that I've produced on statistics, not only the ones uploaded to YouTube. I've uploaded over 100 videos that just aren't available on YouTube. So, I hope you'll check out statisticsworkbook.com. Alright, let's begin. Hello and welcome back. Here now we're looking at another exercise dealing again with two populations, but in this case we're no longer looking at means. Now we're going to be looking at population proportions. So it'd be very similar in the progression as when we went through module 9 and we looked at single population means and then single population proportions. Here it's the same thing. So if you've been following all of these videos, you'll notice some similarities in the process of what we're going to be doing here. So let me just work through the problem, get some context, and then we'll talk a little bit about each step as we go. So tourism plays an important role in local economies of many small towns. Because tourism is a difficult industry to define due to all of the different activities that are involved under the umbrella of tourism, hotel occupancy rates are frequently used as a rough measure of the industry's overall performance. The following table provides hotel occupancy rates for your hometown during the month of August for 2 consecutive years. Okay, so the heading here told us we're doing a one-tail test. How could we know otherwise if it wasn't just given? Well, there's usually clues somewhere. Here it says formulate a test to determine if the occupancy rates have increased. So what I want to do, I'm going to formulate our test here with our null and alternative. Now it's important to note that we're working with proportions, so our notation has to reflect that. I'm not using mu anymore because it's not a mean, now it's a proportion. So what I want to show is that the difference in proportions has increased. So when I hear increased, I think of an upper tail test. So that means that I'm going to define population 1 as this year, or proportion 1 as this year, and last year was it will be proportion 2. So that when I have this difference, P1 minus P2, I want to show that that is positive, which is the same as saying P1 is greater than P2. So that would show that the proportion this year is greater than the proportion last year. So I'll fill in then the null hypotheses, which shows that no, there has not been an improvement. The proportion is no greater than, smaller than, or at most equal to the previous year, and the alternative shows that yes, an improvement has been made, or at least the evidence supports the claim that an improvement has been made. So that's it for part A. Part B, now calculate the test statistic. So here what we need, this is a little bit different from what we've looked at. The test statistic still looks very similar. It'll be the point estimate of the difference divided by the standard error of the difference. And here I'm writing it out a little bit differently because the standard error of the difference in proportions, well, it's going to look similar, but again, similar but different. It's going to be the proportion 1 minus proportion times 1 over n1 plus 1 over n2. Now you might be wondering, well, what is that proportion? I haven't put a subscript on it. There's no 1, there's no 2, as I did up here in the test statistics. So what is it? Well, it's been a while since I've said this, but in many of the previous videos on hypothesis testing, you may remember me saying that we always perform these hypothesis tests under the assumption that the null hypothesis is true unless we have evidence to show otherwise. So again, this assumption is going to find its way into our calculations. And so what that implies here is that we calculate what is called a pooled estimator of that proportion. So we want, it's basically just a weighted average of our two sample proportions. And the assumption here is that if the null hypothesis is true, then what that means is that P1 is equal to P2 is equal to some common proportion. And so if that's the case within the population, that those two are equal, then what is our best estimate of that true common population proportion. And as it turns out, our best estimate is given by this pooled estimator, which is, again, it's just a weighted average of our two sample proportions. So let's get into this, and we'll start doing some of the calculations just in order to get to our test statistic here. So the first thing we need, I don't even have yet my sample proportions, so there's P bar 1, P bar 2. Okay, now I'll get my calculator here. So this is 1498 divided by 1600, so 0.936. And the second one is 1365 divided by 1500, 0.91. Okay, so there we've got enough information there for our numerator. So this is going to be 0.936 minus 0.91 divided by, well, now we need to work on that standard error, and the first step there is to obtain this pooled estimator. So two different ways that we can calculate this. I'll do it the first way, just exactly how the formula is written, and then I'll show you what might be maybe an easier way. It depends on what information you've got. So sample size N1, this is 1600, times that sample 1 proportion, plus this one is 1500 times 0.91, divided by 1600 plus 1500. And that will give us, where's my calculator go? Okay, right there's good. So 1600 times 0.936 plus 1500 times 0.91 divided by 1600 plus 1500 equals, so 0.923. Okay, so there's our pooled estimator for the population proportion. Now, what we also could have done, and here I think I'm going to have a little bit of rounding here, but the way that this was calculated, this is 1600 times that proportion, which I know was 1498 over 1600, plus 1500 over that proportion, which is 1365 over 1500, divided by the total sample size. Oops, that's 1600 plus 1500. So all of this just cancels out. And so if all of those values cancel out, well, why don't I just erase them? And we're just left with that. Do I have room over here? Come down here. So again, this would just simply be, and there might be some rounding error here, but 1498 plus 1365 divided by 1600 plus 1500, and 0.923. So there we go. There's a little bit of rounding error at the fourth decimal, but there we get exactly the same number. So either way, whichever one is easier based on the information you've got is perfectly fine. So and we've got our pooled estimator. I'm going to write that up here, 0.923. Okay, so now I'm going to clear myself some space. And now we can calculate the standard error. So we're still just looking at intermediate steps. I'm going to calculate this one here. So there's our standard error, and I'm going to plug in our numbers. We have our pooled estimator that we just obtained, 923. Times 1 minus 0.923 times 1 over 1600 plus 1 over 1500, and all that square root. So let's get that calculator out again. Come over here. So this is 0.923 times 1 minus 0.923 equals times, open brackets, 1 over 1600 plus 1 over 1500, close brackets, equals, and square root all of that, and I get 0.009, let's round that to 0096. 0.0096. is my standard error, and all that just to get our denominator over here, 0096. So finally, we can obtain our Z statistic. We'll plug that into our formula. So now I'm looking at this calculation up here. So this now is going to be 0.936 minus 0.91 divided by 0.0096, and I get a value of 2.7. Okay, so we have where can I write that? Here's our Z statistic down here, 2.7. Okay, so all of this now we can go and look at our Z distribution, and we want to find the corresponding p-value for this. So here we've got our test statistic, our Z value is 2.7. Now let's go find our p-value. We have here our level of significance is 0.05. So I'll pull up my Z tables, and I have 2.7. So there's 2.7. I think it was just 2.70. So this gives us 0.9965. Of course, that's this area in the lower tail, and we're doing an upper tail test, so I want this region here, 1 minus 0.9965, and so that will give us 1 minus 0.9965, 0.0035. So there's our p-value. So our p-value, 0.0035. Now comparing that to the level of significance that has been given, we have comfortable evidence. We can comfortably reject that null hypothesis because our p-value is less than our level of significance. So here we can reject it. I have sufficient evidence that supports the alternative hypothesis, meaning that it does appear as though we have seen an increase in hotel occupancy rates between these 2 months of August. Okay, so hopefully that all makes sense. There's a few more intermediate steps in the calculations, but again, the process here you've probably seen is exactly the same as any other hypothesis test that we've done. In this case, there's just dealing with this standard deviation or this standard error and having to calculate that pooled estimator for the proportion. But aside from those other little steps, the rest of it I hope you see is very, very similar. Okay, so thank you again for watching, and we'll get to one more problem here in just a sec. Okay, bye-bye.